Rates of reaction. Rate is basically the speed of the reaction. Some reactions are very slow, some are instantaneous, very quick. Reaction rate is expressed in the amount of reactant changing per time. So for us, rate is equal to the change in concentration of the reactant A, which we're going to use brackets for concentration, over change in time. Unit-wise, concentration is measured in molarity, and time is in seconds. So the units for rate are molarity per second. Collision theory deals with reaction rates, and collision theory says that in order for atoms or molecules to react, they must collide with each other. And two things have to be true. Number one, the colliding particles must have enough energy when they hit. And then number two, the colliding particles must collide at the proper orientation. So let me show you what I mean by proper orientation here. With this example equation, I've got silver chloride reacting with sodium. Let's say the sodium atom comes in from this direction, and the silver chloride comes in from this direction. So when they hit, you get an intermediate that looks like this. Now I'm trying to form NaCl. Well, if they hit in this orientation, there's no way to form NaCl. So what happens, they simply bounce off one another. Even if they have enough kinetic energy, even if the first condition is met, they're not colliding in the proper orientation, so they bounce off one another in different directions. And so this is an ineffective collision, which means it doesn't produce the products that I desire, which is NaCl and silver. In a collection of molecules and atoms, you will have ineffective collisions because they will not always collide at the proper angles, the proper orientation. So let's do an effective collision. This was ineffective, didn't produce the right products. Let's do an effective collision. Let's say sodium comes in from this angle. Silver chloride comes in from this angle. When they hit now, your intermediate looks like this. And you can see that I get NaCl right here. That's the product. So if they have enough kinetic energy when they hit, they are hitting at the proper angles. So if they have the proper kinetic energy as well, they produce the products that I desire, which are NaCl and silver. So this is an effective collision. It produces the desired products. So two conditions: enough kinetic energy and proper orientation when they hit. Activation energy is the minimum energy that the particles need in order to react. It acts as a barrier. We're going to look at an energy diagram here. You need to know how to label the parts on an energy diagram, so let me label these parts for you. Over here, you have reactants. You always start with your reactants on the left, and you end with your products on the right. At the top is what's called an activated complex, or a transition state. Activated complex. It's always the highest energy, that activated complex. The distance from reactants to that activated complex is the activation energy. So that E sub A is the activation energy. That's how much energy I have to have in order for the reaction to occur. The activation energy acts as a barrier to get to products. Delta E right here is the distance between reactants and products. So delta E is the change in energy of the reaction. Now this one is exothermic. The reason it's exothermic is because products are lower in energy than reactants are. So it's exothermic reaction. So there's 5 parts to every energy diagram that you would need to label. Once you get to that activated complex, the top of the curve up here, you're in an unstable arrangement of atoms. It's at the peak of the energy barrier. You can either reform reactants or you can form products. When you get to the top of that peak, you can reform reactants as well as form products. So reactions with a high activation energy are slow reactions. So know the parts of the energy diagram. There are 4 factors that affect the rates of reaction, how quickly a reaction will occur. The first one is temperature. If you raise the temperature, that normally speeds up reactions because raising the temperature raises kinetic energy. That means the collisions have a much larger force when they hit, and the number of particles with the necessary activation energy will increase. So increasing temperature raises kinetic energy. Kinetic energy increases the frequency and force of collisions. It will speed a reaction up. Concentration. If you add more particles, if you increase the concentration, it increases the frequency of collisions. You have more collisions because there's more reactant molecules. So that will lead to a higher reaction rate. Particle size. Particle size deals with surface area. The smaller the particle, the larger the surface area. And if I can increase that surface area, I increase the collision frequency. So I want small particles to have a quick reaction rate. And I can decrease particle size by dissolving solutes or by grinding up solids. And then the fourth thing that can increase reaction rate are catalysts. Catalysts increase the rate of reaction without being used up. They allow the reactions to proceed via a lower energy path. Let me show you 2 energy diagrams. One is without a catalyst, one is with a catalyst. Notice the activation energy without a catalyst over here. It's a pretty large energy barrier, but when you add a catalyst, notice what happens to the activation energy. It gets lowered. There's a lower energy barrier, so the reaction can happen more quickly. So catalysts lower the activation energy, and therefore reactions can happen more quickly. There's less of an energy barrier. Catalysts are written above the arrow in an equation, so anytime you have something written above the arrow, like in this case I have Br2, that is a catalyst. Catalysts are written above the arrow because they're not a reactant, they're not a product, they simply lower the activation energy. They don't get used up in the reaction, so they're written above the arrow. Enzymes are catalysts in biological reactions, if you've heard the term enzymes. I can also slow down a reaction if I want to by adding what's called an inhibitor. So an inhibitor slows down, sometimes even stops reactions.